next up we have Stuart Mumford, and you are from Sheffield.
Indeed.
And he'll be talking about SunPy, Python for solar physics.
Yes, so the SunPy project is kind of the same age as SciPy, which sort of surprised me when I first realised it, because there's a lot of mature code in SciPy, and we don't have anywhere near the same luxury of having tools already in Python to build on. So we sort of started from scratch. So I'm going to sort of walk you through the solar physics sort of data types and stuff that are available and the sort of problem we're trying to solve. I mean, some of it will probably be quite similar to like general astronomy, but I should probably just pick up the microphone, shouldn't I? Probably a good idea. Okay, so the sun is probably the easiest to observe star, especially if you're in Texas. And there's an awful lot of high resolution, both spatial and temporal data available for the sun. The NASA's SDO satellite that went up a few years ago downloads about 1.2 terabytes of data a day to the ground. At the time when SDO launched, their downlink connection was faster than my home broadband connection, which made me very sad. So there's sort of two main things that need to be done with solar data. That you need to process it, like in the same way you need to process most optical astronomy data. You need to calibrate it into some, like remove the effects of the instrument and then add some physical coordinates to it. And also then actually do some science on the data once you've calibrated it. That's like what you get paid for, right? That's the idea. So at the moment, this is mostly done, the initial sort of as the guy from SKA was talking about, like some of the processing, depending on what instrument it is done on a server somewhere where the data comes down from the telescope. And some of it is left to like the end user. So at the moment, most solar physics data analysis is done in a package called SolarSoft, which is IDL. So most of the server side and the local processing is all SolarSoft, and most people therefore just use SolarSoft for their physical analysis as well. So for those of you lucky to not know what IDL is, it's a proprietary data language which is quite old, and I hate it. I really do. Okay, it's just right. Okay, so the SolarSoft library is primarily IDL with some other bits written in different languages. But the whole SolarSoft download is about 10 gigabytes installed. It's got a lot of calibration data bundled in with it, which you can't separate out from the code when you download it. It is open source in the terms of you can download the source code. That's about where the similarities with a sort of Python open source project end, as far as I can tell. There's no clear way to contribute to this project. Presumably you have to email people that maintain the code. I don't know, they don't say anywhere. The limit of the documentation is generally doc strings at the top of functions, and that's also the limit of their version control, where every time someone modifies a piece of code, they append their name and what they've changed to the end of the doc string. If they remember, presumably. All the install and update is done using some Perl scripts, which may or may not work depending on what your institution's firewall settings are like. So it's far from ideal, but everybody uses it, and everybody therefore, because they're already in IDL, uses IDL for their data analysis and all of their science. I had a fantastic quote off someone the other day when my friend suggested to him that he start using SunPy. And he was like, but SolarSoft's perfectly fine. Everybody's always used it, therefore it must be correct. Yeah, sure. Okay, so the SunPy project was sort of spawned out of people's realization that IDL and SolarSoft is far from the ideal package to be using. So there was some talk of building a library which was based in GDL, and eventually we came back around to, there was also some talk about building a library based in PDL, which is Perl, maybe worse, and coming back round to using Python, and a few years ago moved on to GitHub, and we've had a couple of ESA Summer of Code students that sort of really helped the project get started. So we have a sort of standard open source Python workflow. We use Git and GitHub, and unlike the 10 gigabyte download of SolarSoft, we've got very minimal data inside our repository, a bit for testing and sample data, and that's it. And we'll never put calibration data in the main code repo. That can go somewhere else. We have decent Sphinx documentation on Read the Docs. One of the largest contributors to our issues list on GitHub is document this, so there's still a fair way to go. I know people sometimes whine a little bit about the Python packaging system, especially if you start adding in C code, but it's a lot better than 3 Perl scripts. And at the moment we have a small amount of C API code. So we currently support 2.6 and 2.7, though I tried my hardest to break 2.6 with the last pull request I put in. We'll try and get 3 working. We haven't sat down and fixed all the bugs, but there's no real reason why we can't make 3 work. We have a reasonably standard set of dependencies, which, apart from NumPy and matplotlib, you don't need to. Oh, and SciPy. SciPy, NumPy, and matplotlib, you need to import the package. And probably pandas as well, actually. And then you need suds and beautiful soup 4 we use for, we've got a VSO module, which I will now tell you about. So the main sort of core features in SunPy at the moment are the virtual solar observatory, which is a Python API to their web service, which is a service that allows you to download data off of lots of different servers where attributed to instruments, where the data comes in from whoever's taken it and downloaded it. And also a front end to the heliophysics events knowledge base, which is a database of events on the sun like flares or eruptions, and which tells you the spatial and temporal coordinates where these events happen, so you don't have to go out and download terabytes of data and scan through it to find these things. You can look them up and download the bit of data that interests you instead. The main thing that SunPy has implemented is 3 data types, 3 main data types, to sort of provide a consistent interface to solar data in general. We'd like to make the 3 types more consistent in between themselves, but they're not as good as we'd like them to be at the moment. Map is for image data, either 2D or 3D, spatially aligned or temporally aligned data. Light curve is sort of 1D with time series. That's what uses pandas, makes extensive use of pandas. And we have a spectrum module which can handle just wavelength or wavelength and time, which was written by a ESA Summer of Code student. We've also implemented solar-specific world coordinate transforms, mainly just transforms between the different versions of coordinate systems that are available. We also have a fit support and a horrific JPEG 2000 implementation. And also we've wrapped up matplotlib visualization into SunPy. So I'll give you a bit of an example of some of the things you can do with SunPy maps. So here we import SunPy. So SunPy AIA 171 image is just a bit of test data. It's just a FITS file in the repo. So that will take, the map factory will take any set of arguments you like, data header pairs, list of FITS files, n number of FITS files as arguments, or URLs, various different things. So you create this AIA object, which then has a plot command. We made plot behave like their respective matplotlib functions. So like imShow, plot returns an axis image object, which you can then use to create a color bar for your image or whatever else you wish to do with it. So this gives you a picture of the million-degree solar corona with a title, which isn't the default one. So also, as I mentioned, there's a way you can download and download data. So this goes away and looks up 5 minutes worth of AIA data for the AIA instrument at a certain wavelength, downloads it all to your hard drive, and then creates a map cube and animates it, which this video, the pants video that it is the reason that I moved my presentation off of out of LaTeX earlier. So I've sort of implemented a few start-stop buttons in Matplotlib, and you can animate your data. And as I said, the plot object returns an animation object, so you can just use the standard Matplotlib interface to save our movie, the data afterwards. So the sort of future directions we're going, me and one of the other core SunPy guys have rewritten most of the map module. We now have an object in map which is ND data stand-in to take AstroPy's ND data object in the near future, hopefully. We, as most projects probably do, wish for better test and documentation coverage. Our sort of map collection objects could do a bit of extra work, like fine image alignment or various other things. We have 2 Google Summer of Code students this year as well. One's working on implementing a database, either local or remote. So every time you call the SunPy data downloaders, it sticks the data in a database somewhere. So if you then call the same data again, it doesn't go off on the internet. It finds it from your local database, which I quite like the idea of having one big database for a group where you end up sort of mirroring the data you're actually using. And also, another student is improving our web services and implementing access to the Helio service, which is similar to HEK, but does more fancy things with the whole solar system, including like working out when solar events are going to get to different planets and sort of things like that. The core, as I mentioned earlier, the immediate goal is to provide and develop a solid base from which we can build more processing routines on top of and try and make SunPy a valid alternative to other solar packages. So we have about 8 people who are sort of core developers, and that on the right-hand side is a list of other people who have committed to the project. So this is all the people that GitHub told me contributed to SunPy. So that's me done. Okay, so the question is what sort of coverage of the SolarSoft library do we have in SunPy? And the answer is probably nearestly approximated to 0. We have, SolarSoft is humongous. Basically, we have a system where if you have calibrated data, you could load it into SunPy and use it for sort of analysis and visualization. We're working on extra routines like differential rotation compensation and sort of those sort of analysis, higher level analysis routines is the sort of first goal. We're going to leave the data processing to SolarSoft until a mission team come to us and go, we've got this code you might like, which we actually have one who's said that on our mailing list, which is an encouraging sign. If you're just doing simple analysis or happy to write a bit of your own code, then it's good for analysis, not so much for data processing and calibration off of instruments at the moment.
You mentioned there about downloading data and caching and stuff. Do you see, the future of solar science getting to the point where it's going to be more beneficial to push the processing to the data rather than the other way around? It's kind of an SciPy question as well about how much should we be looking forward to the future where instead of thinking about the data that's come to me, about building these, as part of building these packages of getting this stuff out there to the data and then just the visualizations coming back.
Yeah, well, the question is whether we should be downloading data or uploading code, basically, I think. Well, it would be brilliant to be able to upload code. It would be a lot faster. But that is dependent on there being a way to execute the code where the data is stored. And
sure, that's part of these frameworks. You could take, it as part of the overview of these frameworks to provide those kind of.
yeah,
It depends where the future goes. I mean, you may not need it. If you're going to see, tenfold increase in your data volumes in the next 10 years, you might need it. If not, you might not.
yeah. I mean, yeah, it probably would be needed because the data is just going to keep getting more and more data. But the sort of one person probably doesn't necessarily use an awful lot of the data, and there's VSO does quite a good job of mirroring the solar data around the world. So you can normally get hold of as much as you want. There's also SDO cutout service, which allows you to just download small bits of images, so you don't have to pull everything in. So that's sort of more in the short term, that's where it's going. People are reducing the amount of volume you have to download to get the data you need. That's sort of what HEK does and the cutout service and stuff like that.
Do you have any tools for accessing, I think it's the LMMSA, the feature database? There's a database of identified features, when there's a flare coming from SDO.
That's kind of what HEK is. It might be the same thing. I don't know.
Maybe it's the same.
HEK runs automated detection algorithms on SDO data and catalogs things it sees. I think there are other catalogs as well, but I don't know which ones it uses.
Are those in near real time? I have a specific goal when I hear that there's been an X-class flare on the sun that's impacted Chandra operations. I want to know where on the sun it was and get a picture of it.
There's
if I can do that with your tools.
maybe not at the moment, but there is a service that does that, right? Yeah, that might be something that I might work on if I ever get a spare 10 minutes. I quite like that idea as well.